Well, hi everyone. Welcome to our virtual road trip webinar series. I'm Molly Soltis with Asphalt Testing Solutions and Engineering, and it's my pleasure to welcome you on board today as we focus on mixed design variations. We're joined by two industry experts who will discuss why the design process is so critical when planning for different mix types. Before I introduce them, let's go over a few housekeeping items. The attendee controls appear at the bottom of your screen. And in the bottom left-hand corner, you'll find the audio settings. If you need to control your speakers or adjust your audio, you can find that here. If you're having an issue with sound, just exit the webinar and then rejoin us. Since you're a webinar attendee, you're in listen-only mode, but later we'd like to allow attendees to be able to join the conversation. So if you have a comment, a question, something to contribute, use the raise your hand icon, and the host will unmute you if time is permitting. If you have a question and you do not want to be unmuted, please use the Q&A box shown here. And you can open that window and type your question in. We'll get to questions at the end of the webinar. So now I'd like to introduce today's speakers. First, we have Tanya Nash. She's the pavement materials engineer here at ATS, and she has over 18 years experience in the asphalt industry. She earned both her bachelor's and master's degrees at the University of Florida in biomedical engineering and is a licensed engineer in Florida and Alabama. Scott Quire is the technical director for Bluegrass Testing Laboratory in Louisville, Kentucky. He has been in the industry for over 30 years, focusing on the design, control, and placement of asphalt mixtures. He earned his bachelor's degree at the University of Kentucky and is a professional engineer licensed in Kentucky and Alaska. So as we prepare to depart, I'd like to thank you all for choosing ATS as your preferred travel provider today. Please take a moment to locate your nearest exit. And please remember, in some cases, this may be behind you. I think for most of you, you can locate yours in the bottom right-hand corner of the screen. So enjoy your trip, everyone.
Okay. Greetings, everyone. And so anyway, today I have the distinct blessing to be with you and to present the thoughts of asphalt mixed design variations. As a mixed design engineer now, actually for closer to 35 years, I've had the opportunity to see a variety of mixtures both throughout my career. And then of course in designing mixes since 1985, from rolling through Marshall designs and Super Pave, and then I've had a lot of exposure to mixed designs in the United States and outside the United States as well. So today we're going to take off and go and talk about variations in mixed types and some of the concepts and thoughts that you may experience. Bluegrass Testing Laboratory, of which I'm the technical director, we're an offshoot of Louisville Paving, and so that's a large paving contractor in central Kentucky. So these are just some shots off some of our jobs, then off some of our friends' jobs. And but as far as when you start looking about asphalt mix types and you start considering all the things they're asked to do and the various stress strain applications that they experience, from the high flexibility of a bridge deck mix to a highway with its major loading, to a speedway with its high lateral shear stresses, to a parking lot that's asked to perform, as it sits there and basically is baking in the sun with embrittlement. So you have a lot of different thoughts you're trying to cover, and given judicious thought to each one of those applications, we can come up with a pavement that should function. So in variations in asphalt mixed designs of asphalt mixtures are where the performance of the mix will start. The design process is critical and has many components that work together to make a design that can be produced, placed, compacted, and performed. And then, of course, our learning objective for this session today is we'll review the different types of asphalt mix structures and what sets them apart from each other. And so with that said, asphalt mixes are utilized, of course, in various applications, from highways, speedways, airfield pavements, parking lots. Optimized pavement performance can be achieved through careful, thoughtful selection of the asphalt mix type. And as designers, more often than not, we're subjected to living in the aftermath as an agency or as an owner throws out what they want, and then we drop into it. Sometimes we're allowed the opportunity to present, the best mix for the application. But anyway, the asphalt mix types we're going to be talking about today are dense graded asphalt mixtures, matrix asphalt SMA mixes. And then also we're going to be talking about open graded friction courses, or open graded mixes, I should say. So when you start talking about dense graded asphalt mixtures, generally we're going to be talking about pavements for highway applications, for airfield pavements, and then of course on other applications, of course, racing facilities, speedways, and road courses, and then maybe parking lots. So for those, I'm not really sure on the experience level of those participating today, but for just going through a couple different takes on definitions for dense graded mixes. A dense graded asphalt mix, which is a well-distributed aggregate gradation throughout the entire range of sieves used. I'm going to give you an example of that here in just a second. Or there's an additional take on it. A dense gradation refers to a sample that's approximately of equal amounts of various sizes of aggregate. Having a dense gradation, most of the air voids between the materials will fill with particles. Dense gradation will result in an even curve on the gradation graph. That they're speaking of a 0.45 power chart. And I'll show you an example of that too in just a minute here. So when you go back to the inception of, well, across the United States, for the most part, on dense graded mixes, most people are living with a super pave mix design system. There are still some states that use Marshall. There are some states that use a hybridization of both Marshall and super pave designs in their variety of mixes that they use in their various applications in their states. But when you start talking about a dense graded asphalt mix, if you look at AASHTO M323, the granddaddy spec of what most states have taken and modified to their own suited needs, this is an example of the gradation control points you would see in AASHTO M323. And it goes all the way from the base mix, these 37.5 millimeter or 1.5 inch mixes, all the way down to a number 4 mix or 4.75 millimeter mix. And of course, as you can see, the things that differentiate each one of these is the coarseness of grading, and each has its own application as well. Also further subdivided in the gradation control bands of M323 is a further sub-designation of a coarse graded or of a fine graded super pave mix. And when you look at the further breakdown, they also define the primary control sieve that if you were, for example, on a 37.5 millimeter or 1.5 inch base mix, if you're below the 47% passed on the 3/8 or the 9.5 millimeter, it'd be a coarse graded. If you were above that, it would be fine graded. And again, within the control points. And of course, you can do the math on these other mix types. But anyway, that would be the division point between a coarse graded and fine graded super pave mix. Also, when you start looking in consideration of the properties requirements for each one of these mixes, for those that are not familiar with mixes, you wonder why the asphalt content, varies as it does. Of course, that for the most part gets into the available surface area. A base mix having much lower surface area available than a surface mix would. So when you start to consider the Vma criteria, for example, the voids and the mineral aggregate criteria, which basically that's just the volume of air that's required. In this case of this specification, it's 4% air voids, plus the volume of effective binder, the effective binder being the non-absorbed portion of the total binder. So in turn, when you start looking at this criteria, you can see that one of the things you can see is the asphalt content variety, or the Vma criteria, which is a function of, trying to ensure that there's a sufficient amount of binder for durability of the mixture. This, for those who are not familiar with phase diagrams, this is an example of a phase diagram. So this helps you visualize when you start talking about, for example, Vma, what Vma actually is. In this case, of course, as you can see, the volume of air plus the volume of non-absorbed asphalt. So one of the functions of the volumetric table is to ensure sufficient amount of voids that the mix will be not in a plastic state, and then also a sufficient amount of asphalt to ensure durability of the mixture. When we were talking earlier about some of the definitions of a dense graded mix, and we talked about a well-distributed gradation, here's an example of a 0.45 power chart. The sieve size is raised to the 0.45 power, and then of course, then they're graphically plotted. But it gives you a visual on what a distribution of what a dense graded mix might look like. I've got a contrast of this dense graded mix versus an SMA mix here in some subsequent slides, and we'll look at that just in a few minutes. But this gives you an idea graphically of what a well-distributed gradation may look like. Also, when you start looking about the varieties of mixes, I had mentioned earlier about, highway applications where AASHTO M323 would reside primarily over highways and pavements at that application. Also, not to forget, many of us live with the FAA specifications for airfield pavements. This is an example of an FAA P-401 specification. This is off a job we had worked on earlier this year. And it's interesting to note that the P-401 specification, that when we went into 2019, they rolled out a new spec. In advance of that, most all the specifications or all the P-401s had been Marshall design mixtures. But then with the new spec, they gave the option of either using gyratory or of Marshall compactor as well. So this particular job was set up as a 75 blow Marshall or a 75 gyration mixture. And one thing to note is that a 75 gyration mix provides quite a bit more compaction than a 75 blow Marshall does. So when you start talking about the selection of aggregate structure, what it takes to stand up under a 75 blow gyratory versus a 75 blow Marshall, it's a little bit different. And so in terms as a designer, as I start looking at specifications, for example, this one here, I would know that I would have a little bit tough aggregate structure if I'm going to attack it with a gyratory design versus a 75 blow Marshall. Also, you'll note too that when you start looking at the gradation of this mix right here, if you were to go back and compare this against an AASHTO M323 mix, this would be defined as a 12.5 millimeter nominal maximum mix. The VMA criteria by AASHTO M323 for that mix is 14. You can see that a P401 is 15. What that's telling me is that it's going to have additional binder required or needed to satisfy the VMA criteria. So one of the things that we experience in P4 or the FAA spec P401 is that it comes at a little higher binder content simply because of the VMA criteria. And then the air voids are fixed at 3.5%. So that pretty much tells you have to have a pretty good volume binder. So when I walk into that specification, it tells me a lot of things: increased binder. Also, if I think about the type of compaction I'm trying to pursue in designing the mix, it also tells me something about the aggregate structure. Also, too, when you look at the P401 spec, it also has a loaded wheel testing requirement, the APA at 250 PSI, 250 pound force loads, and that can be tough on some mixes to pass. So again, in the design, I think about the aggregate types. For example, a mix that has a fairly high natural sand content, typically the 15% is the maximum limit. But if you go in the 10 to 15% range and you have a fairly high binder content, in some cases, the APA requirements can be challenging to pass. This job also had 7622. I just threw that out there. Most of those mixes don't permit ramp. This is just a quick shot here inside of our laboratory. When you start, for those that are not familiar with compaction equipment, of course, the standard design, as we have lived with forever, had been a hand hammer, a manual hammer. And then in turn, you were allowed to use a mechanical hammer if it was calibrated against the hand hammer. And then, of course, the new jobs are also allowing gyratory. So another thing to consider when you select the aggregate structure in, for example, airfield pavement, is that if you look not only from the point of the design, but also ultimately after the design is concluded and this mix is produced, some of the factors you got to live with. For example, when you start looking at the joint density criteria on this one, it's set at 90.5. And the joint cores are cut with the core centered right on the joint. So if you have any degree of segregation, it can be terribly, terribly difficult to pass that specification. Many of these jobs have the requirement where you cut the joints back. That we've been participants and done acceptance testing on a lot of jobs where the engineer more or less didn't cut the joint back. So in turn, the mix as placed then, if it was very coarse graded and you had to cut joint cores, that 90.5% could be terribly difficult. So as a mix designer, I look to see how it's going to be produced, what the components are, but in final placement, what the placement contractor is going to have to live with. So in turn, all those things play factors on how I select my aggregate structure and what this thing's going to look like. minimum VMA is controlled during production on this new spec too. So in turn, you also have to watch, control of asphalt content very closely, not only because of VMA, but also, of course, this asphalt content spec itself. Let's shift gears now. Let's talk about an additional mix that dropped in on as a dense graded mix, the P-404 fuel resistant mixture. And the purpose of that mix is to provide a fuel resistant surface where pavements are subjected to fuel spills. And here's an example of one that we had just done. In fact, about a month ago, we were working on this one. And you notice the binder grade was a PG 82-28 or an 88-22. And then in turn, when you look at the subsequent criteria under there, it tells you that this is a very heavily polymer modified binder. That's what it's designed and intended to be. And so anyway, that's a binder grade that sometimes it's a special request item. Standardly, that's a special produced item that you'd be talking to your binder supplier about. Here's an example of the specifications on a P-404. It's 50 below Marshall, specifically required to be Marshall. Stability requirements, 2,150. If you have a fairly tough aggregate structure with an 88-22 binder, typically to pass that stability minimum requirement is not an issue. But also note too that the P-401 design we just talked about a while ago was designed at 3.5% air voids. The air void requirement on a P-404 is 2.5%. So it's intended to be more impermeable. It's interesting to note that when you look at the Vma criteria, this mix it's 14%. And then that maximum weight by the fuel immersion, the test that we're going to be talking about in a second, is 1.5% maximum. Again, it has an asphalt pavement analyzer requirement on it as well. But when you look at the grading bands on a P-404, and this would be a 9.5 millimeter or a 3/8 inch nominal. If you go back and compare this back against AASHTO M323, the minimum VMA criteria for this mix is 15, yet you can see that the minimum criteria for this one is 14, which would seem to be a little on the dry side. But really what controls in this mix is when you look at the 1.5% maximum loss in the fuel resistance test, that's what really controls, because what happens is that you have to have a fairly high binder content, very heavily polymer modified binder, to survive this 1.5% maximum limit that you saw in that test. The test is actually, these are specimens that are made, manufactured 2.5% air voids plus or minus 0.7. Then they're soaked in kerosene for 24 hours. And then at that, you bring them out, you let them dry, and then in turn you get a final weight on them. But so in the scheme of it all, it's a fairly tough test. And to have a sufficient binder content, a very heavily polymer modified binder is critical. What we've seen of this year, we've seen some problems with some of the tests where the binder supplied would be suspicion to probably have not straight polymer modification, maybe some additional constituents that cause problems in passing the test. And so it was found that heavy polymer modification was essentially necessary to be able to pass the test, and sufficient binder content. So as a designer, those are some things you contend with as well. Again, I'll go back. If you were a designer and you saw that 14% minimum VMA criteria on that mix, you would think I can get by with lower asphalt content. Probably not, because the 1.5% maximum kerosene loss is going to be the controlling factor that'll drive binder content in this test. Again, when you look at the criteria for a P-404, again, you got joint density at 92%. It's a tough number. Again, we're designing the mix for 2.5% air voids, but in turn, it means that there can be really no segregation of the mix on the joints too. So in turn, fine graded mix is really what I'm kind of thinking about here. Let's shift gears for a second. Let's talk about racing facilities. Anywhere from ovals up to road courses. The mix thoughts and concepts that go into that are a little bit different, because we have high lateral shear stresses, and some of the things we're trying to achieve, especially performance in the curves, and then the racing vehicles and how they wear on the joints. There's some things that we really critically need to think about to get good performance on these mixes. The binder grade, typically this is an example of a job out west, and they were showing a 76-22 polymer modified where there's no PPA or no modifiers allowed other than SBS. And you can see the softening points set at 180 and the elastic recovery is set at 70%, which that's pretty, not too stringent, but you know, it specifies that we're going to be using an SBS modification system. 75 blow Marshall. For all the designs we worked on, Marshall compaction is served us well, and it continues to serve us well. So in turn, there's no thoughts to vary off that at this point in time. These are some of the specifics on mixed varieties or the mixed properties that you can see specified. This was a project placed out in California. And so anyway, the reference that was desired by the owner and the contractor was to use a Caltrans spec for some of the numbers that were out there. But then in turn, there were some modifications relative to the racetrack to make it function properly. Mixed placement is always a factor on the mixes, again, as it affects aggregate structure. And so in turn, one of the things we do on racetracks, though, is that we stand there cutting the joints back so that when you cut, the density that you're going to achieve on the mat right there at the joint and then in the area adjacent to that, it's essentially going to be the same number. So you're ensured that you have a very, very good joint density. And for proper performance of the mix, it's critical that you get good joint on these mixes because the racing vehicles tend to work on them pretty hard. Some additional factors we might want to consider about when you start talking about dense graded mixes and things or issues that affect the aggregate structure, the air void target. You know, right now we have many states that have shifted off 4% air voids down to 3.5%. Some states, and one in particular, North Kentucky, has gone to 5% air voids, Super Pay 5. I think, Tanya, you've got a question we're going to talk about here in a minute about that one. But also VMA minimums. We see that, of course, the AASHTO M323 criteria specifies a minimum number. Seen some states, though, that would shift, take the minimum, add 0.5% onto that, which means they want more asphalt. Have seen some even shift towards 1% above the M323 minimums, and that means quite a bit more asphalt content. Also, some states are starting to use the volume of effective binder minimum. Basically, all that is to take the percent VMA minus the percent air voids to ensure that there's a proper volume of binder in there. And so some states have started using that in lieu of VMA and air voids, but essentially you still quantify VMA and air voids. It's just that the number you're going to see in print is VBE. Another factor to consider in the design is, of course, percent recycle. We have most suppliers in our part of the world are using RAP. We have had some that have used RAS, recycled asphalt shingles. That usage is not as prevalent as what it was, but nonetheless, some of the designs are out there, if properly set, thought through, and attacked properly, can provide good service. Stability and flow specifications are still something in play in some states as well. So, dense graded mixtures and issues that affect aggregate mixed binder content or additive needs. Let's also talk about balanced mix design considerations. That's the freight train that's moving across the United States. Most every state, if they've not already begun consideration of implementation of balanced mix design testing criteria or performance testing criteria, they're at least in consideration stages for it now. So for those that are not familiar with the term balanced mix design, it's basically a focus that's been on using performance tests to balance asphalt pavement's rutting performance with durability and cracking performance, and to make trade-offs between the two distresses to maximize pavement performance. So, excuse me. When you start talking about the rutting test, the two tests that were primarily being utilized today are the ones that either being used or thought to be used as the Hamburg test or the asphalt pavement analyzer. And some states are using APAs, but I see a much greater utilization of the Hamburg. Another thing on the Hamburg is that additional baggage you get with it is the stripping inflection point. Some states are in consideration of using that in lieu of the what had been the more historical stripping test like AASHTO T283 or ASTM 4867, the Arkansas retained stability test. There's some tests that had been traditionally used. Some states are looking about using the SIP or the stripping inflection point as an indicator of moisture damage. And so that's some additional things you get off the Hamburg. But the bottom line is on the performance test, as we talk about mixed types, mixed designs, Performance testing has an impact on the aggregate structure, the binder content, and the component materials. Many contractors would like to have the option to use greater recycled contents. Through the utilization of performance testing and then all the factors that go into the development of that mix design, it can be proven through the performance test, the index-based performance test, that you can provide a good mix that will give service life. So anyway, balanced mix design is something that we're all grabbing heartily and mightily and trying to gain further understanding on. On crack testing, of course, is a semicircular bend test. This is an example of an I-fit curve over here on the right. And then also the ideal crack test. That seems to be the test that's gaining most traction simply because of its simplicity. And many states are trying to go through and, baseline their mixes right now to see what they have. Then as we go into balanced mix designs, to where we go from a volumetrically optimized design to a balanced mix design, optimized design, we see that, of course, you can establish and see what your ideal numbers can progress to. Shift gears again. Let's talk about the other mix type, one of the other three that we were talking about, the stone matrix asphalt. And what it is, it's a gap-graded asphalt mix that's designed to maximize deformation resistance and durability by using a structural basis of stone-on-stone contact, or an asphalt mix with a high coarse aggregate content, typically 75 to 85%, a high binder content, typically higher than 6%, and a high filler content, typically it's at least higher than 8% by weight. So when you start thinking about what would constitute the aggregate structure, this is the AASHTO M325 table that you see right here. And anyway, it just shows that it's a really coarse blend. When you look down here on the fore sieve, it's very, very coarse, as you can see. The specifications on an SMA, you can see right here. Again, it's got a very high high VMA content, high asphalt content. And so also the other criteria drop into play. So this is just a quick graphics. So when you start talking about a dense graded mix versus an SMA, and we start talking about a well-distributed aggregate gradation versus one that's gap graded, this can kind of give you a graphical thought, conceptually what that might look like. Open gradeds. This is an example of an open graded. This is there on this one vehicle is driving is on a dense graded mix. This is Interstate 65 north of Nashville. And that's a dense graded mix on the left. This is an open graded. And it was a torrential rainfall. And there was no standing water at all on the open graded. So it kind of gives you an idea how well they can function. And anyway, it's the types of open graded mixes that were like open graded friction courses, porous parking lot mixes, and then asphalt treated permeable bases. Typically for an asphalt mix to have an open graded, it's going to have a very high volume of voids, 18 to 22%, so the water will rarely pass through the pavement. When you start talking about open graded friction courses, it's basically designed to promote skid resistance, provide rapid pavement drainage for the wearing course, reduces tire noise, and then also relative to urban heat island effect, it's also shown to be a contributor to the reduction in temperature. When you look at the typical design methodologies are out there, ASTM D107064, ASTM D7064 is a standard design practice for open gradeds. Then there's the NCAT practice, 99-3 design of new generation open graded friction courses. This is an example of the grading band out of ASTM D7064. This is a very, very coarse graded mix, as you can see, with very few fines on the bottom end. So it supports a very high air void structure. This is an example of the South Carolina DOT spec for section 409. And again, you can see the binder content ranges and then the gradation bands 0 to 4 on the 200 and very coarse on the 4. Open graded mixes, when you start also looking about other applications of open grades, porous parking lot mixes, they've gained a lot of traction over the past many years because where agencies or municipalities are trying to keep from tying up available surface areas with storage water detention, they're trying to use subsurface areas for that. So the porous parking lot mixes and then the subsurface areas for water storage have come into play in many places, many municipalities. This is an example of some of the grading bands you can look at for like a porous parking lot mix. So in conclusion, there are a variety of asphalt mix types that have specific applications. Careful selection of the appropriate mix will help ensure optimum pavement performance too as well. And again, I'll say thank you for the opportunity to be here. And I was telling Tanya and Molly, this is a mountain north of Bozeman, Montana, one of my favorite views. So with that, my friends, it's been good to talk with you. And I think Tanya and I have got a question and answer session we're fixing to get into.
Okay. Well, thank you, Scott. That was fantastic information. And I know that a lot of us needed some review on some of it, and some of it was new to some people. So it was a great overview of the different types of mixed designs that are out there. And as we all know, the people that deal with a lot of the mixed designs, there are several more variations that you could probably go on about. The list is long. I was just going to start with a conversation about some of the idea of, you had mentioned the SuperPave 5 design methodology. So it's still the same types of designs. You know, you think about your big three that you did: dense graded, gap graded, and open graded mixes. But the methodologies of design seem to be constantly changing. So you went from Marshall to SuperPave. You've got a guideline in AASHTO, but I'm not sure how many people really follow AASHTO to the letter. I think everybody has a little bit of a twist on it. Same thing with the Asphalt Institute or even the NAPA guidelines. So I was just going to ask you a little bit of your thoughts on, when you're faced with some of these new design methodologies, like the balanced mix design that's coming out, what do you do? What's your first approach to looking at something as a new specification or a new process in order to get a different design out?
Well, and looking at the specifications, if the agency has set limits for me, that helps a lot, because it might tell me, you know, it points me in a direction of how outside the box or how aggressive I may have to pursue the design. For example, when you and I were talking earlier about some of the ideal CT index numbers in Florida versus some of the ones we may be finding here in Kentucky, you know, we have numbers that typically are in, 120 to 150 range on ideal CT index testing, in variance with what I hear Missouri, and you talking about Florida and Alabama, some numbers about in that range where, you know, there's numbers in a 20, 30, 40 range. They're major contrast to what we have. So as I walk in, if a contractor were to call me with numbers where he's wanting to approach 100, he's living in an area where he's got 40 or 50, you start thinking outside the box. So as a designer, I know binder content, for example, is going to help them cracking a great deal. There's other things that might come into play. Also, we live in a world where high recycle contents, most because of mixed economy, most contractors are going to want to try to use some degree of wrap. In some cases, they want to explore the limits. And like I said, on a NAPA wrap webinar, we've had some 60% wrap designs on surface mixes that we pull off very successfully. And they've satisfied performance tests in really great fashion. And they have, you know, this be like year 3 production of those mixes. So they can work. But as far as the thought process, as a designer, I know that typically they're going to come with higher binder content or some sort of modification system. So the spec really helps point me in the direction of how aggressive I need to be in thinking outside the box. I don't know whether that helps any or not, but.
It does. Maybe we'll talk more about very specifics. But we do have a question from Jeffrey Anderson, who's asking, when using RAM or recycled asphalt material, would you accept 100% of the binder as effective, or should a percentage of the AC % from the RAM be used for wrap, frap, and RAS?
I agree. I know where the young person's going with. I agree totally. For example, on wrap, that the thought that 80 to 90% of the available binder content only comes into play, and the rest of it lies in like an inert black rock. That's a terribly good thought. And if we're trying to keep from creating dry, really need to give consideration. In fact, on RAS, I've heard the numbers on the order of like only 50% of the available binder coming into play. So if we're trying to be responsible, and I think that's the word we need to grab here, is responsible designers, then in turn we have to take those things in consideration. Now, obviously, if you're also responsible for mix production and you give 50% credit for a RAS mix, and then you have to test it in the field or using solvent extraction, you better have, there is a couple of design systems out there that help you correct for corrected optimum asphalt content. So in turn, mixed production becomes questionable on how you deal with it. So there's things from the design to production side that you have to take and put together as a system. You do. But I agree with this question. Yeah.
Yeah, I guess my add-on to that, though, as you start doing that, for design purposes, yes, I agree. By the numbers, you can give a percentage credit, less than 100% to your recycled material binder. But then as you're checking grades, for instance, a lot of people are looking at that extracted grade. What do you do in the sense of now we're comparing a false 100% contribution because you extracted it versus what you're trying to do and contribute to the mix portion as a whole?
If you take the recycling question and extract and recover the binder out of it, and then you've got a virgin binder that you're going to be blending with. So if you think that, for example, on RAS, I'm only getting a 50% credit. So if you're doing your binder volumes that you're going to blend, then you're going to test for your binder testing, work on that from that perspective. You actually can control that number from that perspective. Now, of course, the performance test coupled with that are going to tell us a great deal,
Okay. We do have a comment kind of from Greg Reeder. It says, we shouldn't forget about the influence of aggregate quality properties on the overall performance of the mixtures. Particle shape and fractured faces and other properties like the LA Rattler aggregate consensus properties can have heavily influence the overall performance, especially as we move forward towards the balanced mix design and higher recycled contents.
Would agree with that. I saw one this past summer where we changed fine aggregate angularity changed about 3% to two different man sands from the same source, and it changed ideal CT index numbers 8 units, everything. So aggregate properties for sure can influence the testing results well on cracking, and then in turn it has an influence on the Homburgs too, or APAs if you're using APAs.
Okay. And I see Barry Nunez, you have your hand up if you would like to unmute and ask your question.
First of all, thank you for a great presentation, Scott. In looking at all this, I did learn a few things about some mixtures I've never had the privilege of working with, such as racetracks and things like that. But also, I wanted to ask you, I'm in the state of Louisiana, and we've been approaching balanced mixes a little bit differently. I never even knew what the term was, so I sat on a little task force meeting with the feds recently, and what we're calling it is performance engineer design, whereas we hold on to 3.5% air voids and the VMAs and the volumetrics, but we must prove that the mixtures pass the performance testing, as opposed to the performance testing affecting the optimum asphalt content. Have you heard much about this anywhere else, or are we the only ones down here doing that?
No, when you start looking at the 4 approaches, and that there's AASHTO put out the draft practice and the draft specification for balanced mix design. When you look at the draft specification or the practice, there's approach A, B, C, and D. A would be essentially where you're talking about where you're trying to make performance testing live in a volumetrically optimized mix design is what you're doing, versus the type D, which is one fully optimized by balanced mix designs concept. So your performance testing will tie you down to the asphalt content that's going to get selected. Whether you choose to verify volumetrics, that's baggage on the tail end, and that's a type D approach. And so in turn, I think that's where you're essentially trying to want to go is a type D, it sounds to me like. And I think it's where many of us would like to go, but since this is a new concept to so many people, we get comfortable about living within these little walls we've got of 3.5% air void, 4% minimum VMA, and then we drop a performance test in and see if they work or not. But when you start going to type D, all the walls fall away. It's all performance testing then. And I think that's kind of where you're talking about going, I think, isn't it?
Maybe eventually, but right now, this is where we're at. So thank you for that clarification, because I never knew that. Appreciate that.
That's fine. Thank you for the question.
We have a question from Akihiro Nagasawa, and his question is there any unmet needs, such about SMA or open graded friction courses, for example, workability and OGFCs?
We don't, well, honestly, we don't use that. I know that in Kentucky and Indiana, this part of the world, we don't use many open graded friction courses. We're using primarily dense graded and of course SMAs. That's where most of the mixes are. As far as workability aspect, I can see where especially with the degree of angularity, the aggregate comes into play, that could be an issue. You're talking about trying to utilize additives to help promote that, or what?
I could hear, if you would like to unmute, you may. Starts to talk.
So, thank you for your great presentation. So I just wanted to know the unmet needs about the SMA and OGFC pavement method. So such as workability or hotspot and drain down. Have you ever heard of this thing about SMA and OGFC drain down problem, thing like that?
Well, of course, you can use fibers for drain down aspects. I know that, for example, of course, I'm more inclined to shift back to SMAs on drain down problems where we have the very, very high Vma criteria, high binder contents that go with that. And of course, an open graded, by my best take, is just basically an SMA minus the mastic. That's about the best explanation I can throw at it. But on drain down, of course, some people are using warm mix technology with chemical additives. They're reducing temperature, and in some cases, they're dropping the fibers altogether, and that they satisfy the drain down criteria that way. And so with reduced temperatures, polymer modified binders, I know out in Missouri, we had many experiences with GTR modified binders, no fibers, warm mix, and it worked.
Thank you. Thank you.
Yeah, I'd have to agree. I mean, we deal more with open graded friction courses here in Florida than we do, we don't do SMAs in this state, but the open graded friction courses, really the dire need is to work on the durability aspect. You know, the permeability does great. It's a great, very high air voids, but then you have to work on whether or not it's going to last as long as a dense graded mix. So it's a kind of that trade-off between that really coarse open structure and versus your dense graded, you know, workhorse of your structure, your pavement. So there has been back and forth. I've seen open graded friction courses go down without fibers and have great performance, no drain down. But again, it's kind of similar to what Scott's saying. There's a warm mix involved in it, and or a couple of different additives that help that aspect to it.
Tanya, a question back to you from me, back to you.
Okay.
Is that, and your fibers are using down there in Florida, are they cellulose or are they aramids fibers?
Cellulose or mineral, one or the other.
Okay. I can't help but wonder on the durability aspect of the aramid fibers. We've had quite a bit of experience the past few years up here. They are a wonderful product. Now they bring a cost, but then in turn, they're really good products. I can't help but wonder that in conjunction with the high binder contents, if you couldn't have a fiercely tough surface that way.
We are actually looking into using them.
Yeah.
I know there's a couple of test areas that they're looking into actually putting them down. So it's not off the table. I think it's just that we haven't had a lot of experience with them. So speaking of fibers and modification and all the extra things that everybody wants to put in our mixes. Mm-hmm. So every time the new additive comes out, it seems like we got to try and almost reinvent the wheel on a design process or how to attack the design with the way it performs with the additive. So do you have any thoughts on the importance of possibly the binder testing or the binder properties, especially the blended binder properties, in conjunction with the actual mix performance properties? Should they go together in this balanced mix design process?
I don't think that most agencies are reluctant to want to let go of what the binder's doing. If nothing else from that perspective. Now, of course, we're really going to hold our hat or hold great stock with the cracking susceptibility, the rutting susceptibility. Most agencies, though, they're going to want to know what the binders are actually doing. when we put it together, when it all goes into the big magic machine and it all comes out, Tanya, I guess we're all going to sit with great interest to see how that turns out. But right now, we're really banking on the performance test to dictate whether the mix is going to work. Most agencies are reluctant to let go of the binder side of it right now. So in turn, I think we're compelled, to, at least for the time being, to look at that, I believe.
Is it something that the designer should be responsible for? I mean, as we kind of start getting all these modifications going in, should we be looking at the idea of running those aging tests on the binder, looking at the, you know, the LAS type of test or the Glover Road type of test to really kind of correlate where our performances are going?
40 or 60-hour aging, you know,
Yeah.
lots of things to think about, you know, on that side. Those are still, I've had much discussion recently, but it seems like it's not landing anywhere in agency thought, at least for the second it hasn't. But in turn, I think it deserves consideration to do. Yes, ma'am.
Okay. Well, since you have brought up the agency aspect, is there any gaps in the information maybe that are coming from somebody who has probably worked with both sides extensively? You know, you work with your DOTs, I know, and the idea that, you know, we're designing to specs. We're designing for the owners, which are primarily these agencies, and the idea of possibly that reluctance to using a new type of mix, even though you kind of see it in other states, and the concept or the idea is, oh, well, that's the other state, it's not our state. Is there anything that you can provide that would possibly give the agencies a better way to approach a new mix design or a new concept?
If the agency has faith, if they have faith in the performance test parameters, I know many agencies are trying to make a selection right now. What is the right number? But, you know, if you look at from their perspective on rutting, if you're looking at a Hamburg or 12.5 millimeters maximum rut depth at a given cycle pass, there's one confidence check. On cracking, whether if you're in Florida and you think that if I can come up and hit plus 70 on an ideal CT index test, I'm going to be sitting like gold. So if I know some numbers that are out there, and I know that if I plant 100 on one of those Florida mixes, that's an extraordinary reach. But in turn, if I can do something like that, I would have to think that the agency would probably turn their heads and take great interest in things like that. So I guess the numbers that are presented, and if you're using performance tests, I think that's how I'd have to attack it. I know that in this part of the world, that's how we're approaching all the agencies, is with performance testing, and then in turn presenting by our best take credible numbers and not some arbitrary low number that, you know, really is not going to gain us anything. And we need to raise the bar. We do.
Okay. Grant Rollenhoff agrees. Delta TC. It seems like that's the way he feels like it should go. So
Hey,
he just made a comment. My only last comment to you or a question would end up being saying, you know, with the future in mind, as the new designers come up, you know, new breed of mixed designers come through with all the new technology, the new tests, what advice do you have for them?
Run a lot of tests. We jumped into our first ideal CT and Hamburg jobs. I've been doing Hamburg testing since 2012. And as far as crack testing, we jumped in when the state of Kentucky identified the need, and Buzz Powell did a presentation, KDOT jumped on and said, this is life. This is what we're going to do. So we jumped in, and part of our contracting group, we did the first performance job in Kentucky. And we learned a great deal off of it. But as far as all the testing is from that point to what we've done since then, we've done a tremendous amount of testing, both of our own mixes and then for other contractors and for other binder suppliers, is trying to establish and get values. And so in turn, that's helping us, like Tanya, when you and I were talking, our Kentucky world, a typical 100, 120, easy numbers, you know, that's just where we are. Then in turn, when the Airfield pavement that had the helicopter landing pad to where all the drug interdiction helicopters landed and they were rutting all the time, they said, give us something that won't rut. So that's when we come out 7622 and aramid fibers, we get a 275 out of it, you know. So it's good to have all that background. So I would say, as the young designer, give them the opportunity, run a lot of tests, establish numbers. And if you're not confident about if your mix is good enough, what can you do to improve those numbers? And there's things you can do to improve higher binder contents, maybe additives and things like that. The higher wrap mixes, we're all exploring those. And in fact, trying to reach the crescendo levels of how high can it go, and we put out a good quality mix. So the performance testing is really being examined heavily from that perspective. Yeah.
Okay. And I think we have time for one last question from Barry Nunez, and he's asking, why do you think that the FAA chose the APA when most are using the Hamburg?
That's a good question. I'm hanging with you on that one, man. No, I question that too as well. Although the 250 pound force, 250 PSI hose pressure test, it's a tough test, man. It is. Of course, you don't have the element where you're running it underwater. Anyway, no, that's a good question. But in turn, I also heard that we just barely escaped maybe having a DCT test running on that FAA spec, so we're all kind of wiping sweat off our brow now. And so.
I heard the same. So, well, Scott, I think that was the last of the questions, and I think I'm good on my questions. I don't see any other hands raised.
I appreciate the opportunity, Tanya, to speak with you.